Hello everybody. In this video we're going to start the discussion on the degrees of freedom analysis, which is the tool that we use to do a more systematic way of solving mass balance equations. The degrees of freedom analysis is a very simple analysis, and it's a procedure that we follow to answer a very important question, which is are the information that we have enough to solve the problem or to calculate the unknown variables or not. And this is very important because it will save a lot of time. So if you can tell from the beginning, before you start the solution, that the information are not enough, then you will not start until you know that we have enough information. So you will search for more information, you will assume something, but you will do something to make the problem solvable. This is before you start. Otherwise, you will start, go through the solution, put all the equations, substitute, and try to solve the equations, and they're not going to be solved together. So this is a very important thing and very big time saver for you to answer this question before you start the solution. The analysis is very quick, and it requires, which is very important thing, it requires that you have a flow chart that is well drawn, and it includes all the information on the flow sheet. This information includes all the flow rates and the compositions that you know, and it includes also all the variables, whether they are known or unknown, and we will see later why this is important. The degrees of freedom is a very, as I said, it's a very simple analysis, and it just includes counting numbers and adding and subtracting some numbers. This is how it's done. So the degrees of freedom is calculated using this equation that we see here. So the equation states that the degrees of freedom equals the number of variables minus number of given variables minus number of equations minus number of additional relations. The number of variables that we have here, it's all the variables that we have, whether they are known variables or unknown variables. So this is what we mean by the variables. The variables can be flow rates, can be compositions. We will discuss this in details at the end of this video, but let's for now agree that this is the number of variables, all the variables, known and unknown variables. And now we have the number of given variables, which are the information that we know, whether we know flow rates, we know compositions. This is something that we count as well, and we put it here. And now the number of equations, which is, we said before, the number of independent equations, mass balance equations, which is equal to the number of components involved in the unit that we are calculating the degrees of freedom for. And finally, the additional relation, which is something we covered in the previous video, and we said that it is a relation that we have between two variables, and it's an extra equation that we can use to solve or to help solve the problem. So it's as simple as putting the four numbers and doing the math, which is subtracting the three numbers from the first one. Before we proceed, I just want to talk a little bit about the philosophy of the degrees of freedom, which is a very important thing, and I believe this is a very helpful point to understand, because it will make it more logical, and it will make much more sense when you understand this, and you'll understand why the equation is put in this way. Why are we subtracting these three terms from this term? So we said that the number of variables, the first term here, is equal to, it represents all the variables that we have, whether they are known or unknown variables. The second term, which is the number of given variables, and it represents the variables that we know. Okay, so the first term represents the number of variables that we know and the number of variables that we don't know. The second term represents the number of variables that we know. So let's say I have 15 variables in my problem, and among these 15 variables, 10 are known. So I have 15 variables and I know 10 of them. So if I subtract the 15, which represents all the variables that are included in this problem, and subtract 10, which are the variables that I know from all the variables, which is 15. So 15 minus 10 is 5. So this 5 represents the unknown variables. Okay, it's very, very, very simple. I have 15 variables as a total, and I know 10 of them. So the rest of the 15, which are the 5, represent the information that I don't know. It's very, very logical. So the difference between these two terms is the number of unknown variables, which is the number of unknowns, if you can put it this way, in a mathematical way. So these two terms represent the number of unknowns. Okay, and we agreed before that if you want to calculate 5 variables, then you need to have 5 equations. So the number of equations must be equal to the number of variables. The equations that we have that can we use in our solutions is one of two types: either mass balance equations, which is in equals out, or if there is a reaction or addition, consumption or generation, so it's a mass balance equation, or an additional relation, which is an extra equation that is given to us that we can use in addition to the balance equations. And this is what we have here. We said that these two terms represent the unknowns, the number of unknowns, and these two terms represent the number of equations that we have, whether they are balance equation or additional relations. So this is what it means, and this is why we do this subtraction, because we need to know if there is or we need to know the difference between the number of variables and the number of equations. Of course, we would love to have the difference to be 0, and this is what will make the problem solvable, that we have number of variables equal to the number of equations. This is going to be the reason for the next slide, when we look at the options for the degrees of freedom, whether it's positive or negative, and which one is or what it means if it's positive or negative. So this is the point that I want to make here. There is one more thing about the degrees of freedom, which is these two terms in the textbook, which is Felder's textbook that we use in these videos. These two terms are combined together, which is the number of variables minus number of given variables. They are combined together in one term, which is called the number of unknown variables, which we just said. I said that the variables are the total number of variables, and the given variables are the variables that we know. So the difference is going to be the unknown variables. So it's not put this way, it's put as 3 terms only: number of unknown variables, number of equations, and number of additional relation. So why am I putting it this way? I'm putting it this way because when I was an undergraduate student, I used to when I took this course, we were taking the course or we were using a textbook. I don't remember the name of the textbook, but the author the author is called Reclitus. It's a very famous textbook. It's a very classical one, and he used to put the degrees of freedom, or calculate the degrees of freedom, this way. He broke the number of unknown variables into the number of variables minus number of given variables. So I'm more used to this, so I like to use it this way. In addition, for me, this is a personal thing, that it reduces the possibility of making mistakes. So it's easier for me to count all the variables and to count all the given variables, instead of picking the unknown variables from different streams. So it's totally up to you. If you're more happy with doing what I'm doing, it's fine. If you are more happy with just calculating or counting the unknown variables directly, it's fine, as long as you're doing it correctly. This is the only constraint that we have. So now for the degrees of freedom, the options of the degrees of freedom analysis, it can be 0, which means that the number of equations equal to the number of unknowns, which is good news. In this case, you can proceed with the solution. It can be positive, which means that you have number of variables larger than the number of equations, the number of unknowns larger than the number of equations, which means that you need to find more information, whether more given variables or more relations or whatever, anything that you can use to help you solve the problem. If it's negative, it means that you have less less unknown variables than the equations, which means that you have redundant or dependent information. So it's called over-specified in this case. There is one point that I want to discuss regarding the number of variables. So this point is about how can we count the number of variables. We have here a stream that consists of two components, A and B, and I have the same stream defined in three different ways. The first is using the total flow rate and the mole fraction of A. The second is the flow rate of A and the flow rate of B. The third is the total flow rate and the flow rate of A. And now I want to check if I can find the rest of the parameters using the two information that we have. So if I know that it's only two components, then I can calculate YB, which is 1 minus YA. And from YA and YB, I can calculate the molar flow rate of A and B, which is Y multiplied by N total. It's very, very, very simple. For the second stream, I can calculate the total number of moles by adding these two numbers, and I divide each one of them by the total to get the mole fractions. So I now know everything. For the third stream, I have the total flow rate and the flow rate of A, and I can do the same. I can subtract NA from N, which will give NB, and then I can get YA and YB from these numbers. So the take-home message of this is that I can define the stream, fully define a stream consisting of two components using two information, no matter what these two information are, as long as they are independent information, meaning that they are not dependent on each other or on anything else. And for example, I cannot define the stream using YA and YB because YB is dependent on YA. So it's just one piece of information, not two. So I have a flow rate and a composition, two flow rates or two flow rates. It's totally enough for me to define the stream, and the rest of the components that I can calculate are called dependent information. Okay, so it's like the dependent equations and independent equations that we discussed before. We have also dependent variables and independent variables. So the variables that we count when we do the degrees of freedom are the independent variables. The point that we want to make here is how to count the number of variables, how to count them. I'm again looking at this term. It's just counting number. I'm not saying which variables. I'm just counting numbers. So for a stream like this, to count the numbers, you just need two variables. You just need two variables to fully define the stream. And if you know these two variables, the stream is done. And you know everything about the stream. So the number of any two independent information are enough to define the stream. The rest of of variables are dependent. So when I count the number of variables in the degrees of freedom analysis, I don't count all these 5 variables. I just count the independent variables, which are 2. The number is equal to the number of components. So if I have 3 components, I have to have 3 variables. I will have 3 independent variables. If I have 5 components, I will have 5 independent variables. So this is a very important thing. It's like when we have 3 components, we can write 3 equations and we can write the total balance. But we said before that 3 of them are independent and 1 is dependent. So the same here. I have 2 components. I can define the stream using many ways. I can define it using mole fractions, number of moles. But to fully define the stream, I need only 2 information. So 2 variables are required to define the stream. So when I count the number of variables, it is simply equal to the number of components, which 2 variables, we'll look at this later when we do the solution. But for the time being, when we do the degrees of freedom analysis, we just only count the number of components. Okay, so this is for the degrees of freedom analysis. So the number of variables in a stream, it is the total number of independent variables involved in the system. So if I have 2 streams, I will count the number of components in the first and the number of components in the second, and the sum is the total number of variables that I have. So this is all what we want to discuss here about the degrees of freedom. Next time we will solve problems, and things will get much clearer when we solve the problems. So I'll see you then, inshallah. Goodbye.